Hi everybody, welcome to test 4 review in differential equation. As always, the list of the questions that we've done is on the top, and on that side will be the important information. Right, I just go right into it. The first question, singular points. So to get the singular point by the definition here, the definition is for the equation in the standard form, so we change that into the standard form. We'll divide by x times 3 minus x. So we do that. And we will have y double prime 3 minus x cancel. We have just 3 over x y prime plus the x cancel out. We have 4 over 3 minus x y. Now this we have is p of x and q of x, and p of x is this function is analytic everywhere except for x equal to 0. So we say px equal to negative 3 over x sorry, this is 1. I don't know why I have 3 there. The 3 minus x cancel out, just minus 1. So minus 1 over x, and this is analytic except for x equal to 0. And q of x is the x cancel out. We have 4 over x3 minus x. This is analytic except for the x equal to 0. Actually the x cancel out, sorry, so there's no x here. It's analytic except for x equal to 3. So the functions p of x and q of x are not analytic when x equal to 0 or x equal to 3. Pretty much is undefined for these values. So those will be the singular point. X equal to 0, x equal to 3. Sorry, this was 1 and there's no x here. So that's the first problem. Next, we'll classify the singular points. So these singular points will be either regular and irregular point. Once again, the definition is on that side. So let's go to 3. First, we'll find the singular point. First will be similar to what we just did. Divide by x squared x minus 2, x squared x minus 2, x squared and x minus 2. So everything cancel out. We have second derivative plus x minus 2 cancel out, will be 3 over x squared, and there's nothing cancel here, so we still have 1, the y prime still here, 1 over x squared x minus 2 y. Right, so divide by that. That's why we have 3 over x squared y prime and 1 over that y. Now obviously this one undefined when x equal to 0, and this one is undefined when x equal to 0 or x equal to 2. Those are also the points where the function are not analytic. So to save space, I will just say that p of x is 3 over x squared and q of x the function analytic except for x equal to 0, x equal to 2. So we say it are not analytic. I mean both of them. It's not a perfect way to write this because this one is not analytic at 0 and this one is not analytic at both of them. But point here we just find a singular point. So once again I should say this one at this point are not analytic and the function at so those are not analytic, right? Because 2 is in here is perfectly fine. Sorry for the confusion. Anyway, the singular points are correct. Now we will classify them. To classify them, we'll find the capital P of x and capital Q of x. If both of them are analytic at the point, then it is regular singular point. If it is not, then it is irregular. So first we do at x equal to 0. We find capital P of x will be x minus 0 times little p of x. 1x cancel out, we have 3 over x. Now, if we put 0 for x, the function is undefined, therefore there will be no series representation, meaning not analytic. So this one is not analytic. Or not analytic at x equal to 0 because you put 0 in here, it is undefined. Or we can also say that this function capital P of x is analytic everywhere except for x equal to 0. That also acceptable. But regardless, when x equal to 0, this is undefined, not analytic, and one of them not analytic, so we can say that x equal to 0 is irregular singular point. Now we go to x equal to 2. Find the capital P find capital P of x. Will be x minus 2 times little p of x. By the way, the formulas again is here. We have capital P of x, that, and capital Q of x, that. Square times this p of x, 3 over x squared. Right. Don't have to do much, but if we put 2 in here, we're going to have 0. Bottom line is it is 0, which is defined because 2 at the bottom is perfectly fine. So this one is analytic at x equal to 2, so which is good. We have to move to capital Q of x. X minus, oh sorry, the p doesn't have the square. The q will have the square. Sorry. Right. The x minus 2 cancel out. We have just x squared at the bottom and x minus 2 on top because one of the factor cancel. Now put 2 in here, it is still defined. It's still analytic. So both of them analytic at the point, so it is a regular singular point. If one of them is not analytic, it is irregular singular point. So we have x equal to 2 is a regular singular point. Right. So once again, we need to find capital P of x and capital Q of x. If both of them are analytic, then the point is a regular singular point. And it is analytic at the point. Of course, if we put 0 in here, it is undefined, but we check for x equal to 2 though. So yeah, it is defined at x equal to 2. Right. So that is 3. Next, the initial equation and initial roots. So that is initial equation. So we have P naught and Q naught. The P naught is the limit of the capital P of x, and the Q naught is the limit of the capital Q of x. Anyway, in the formula of P naught and Y naught, I mean P naught and Q naught, there we need to have the point, and those point is a regular singular point. So pretty much we need to find a singular point. So first let's divide by 2x. So we write the equation in standard form. Double derivative minus 3 plus 2x over 2x. And let's put the parentheses here. Right. Now obviously this is P of x and this is Q of x. And when x equal to 0, both of these functions are not analytic. So singular point is x equal to 0. We should check to show that it is a regular singular point, but for the initial equation it must be irregular. It must be regular singular point. So we don't need to check. We should, but it's going to be a regular singular point. So that's an initial equation. Anyway, so we find P naught is the limit x goes to x naught, x minus x naught, P of x. Then we'll take the limit of x go to 0, which is x naught, x minus 0, P of x is this. And we have the x cancel out. So we just have negative, pretty much have that over 2. If we have x equal to 0, we just have negative 3 over 2. So this limit equal to negative 3 over 2. Now we find Q naught. Limit of x goes to x naught, x minus x naught square, qx 1 over 2x. X naught is, I should write just qx first to be a little consistent. So limit x go to x naught x minus 0 square qx 1 over 2x. Those should be 0. So I have x squared times 1 over 2x. 1x cancel out. And that when x go to 0 is equal to 0. So pretty much we only have the p naught is negative 3/2 and the q naught is 0. We put everything in the initial equation. R minus 1, p naught negative 3/2 r plus 0 equal to 0, and then we solve it. That should be simple. So r squared minus 5/2 r equal to 0. Factor out r. So we have r equal to 0 and r equal to 5/2. So the key point here is we have to find the singular point. Once we know that, find the p naught and the q naught using the limit. When x goes to x naught for the capital P of x, capital Q of x. Once we know those values, put into the initial equation, the form of initial equation is on that side, and then we solve it. And it should be simple. So that was 5. Next we go to 6. Note that this kind of question will not be on the final because it's just too long to do and too many little things that goes into it. Alright, anyway, so first we see the problem. They say that x equal to 0 is a regular singular point. So we know that we're going to use the Provenience method here, which is still on that side. Sorry, that side. Anyway, so we let y equal to n equal to 0, infinity a n x to the n. That's usually what we do for the ordinary point. Now we multiply x to the r into it. Later on we'll factor that out. But for now, just multiply the x to the r inside. We'll take derivative. The n minus r is the power going down. And this minus 1. Next, the second derivative, we're going to take this down and then original power minus 1. The difference between this and the ordinary solution is that the index will shift from 0 to 1 and then to 2 for the ordinary point. This is regular singular point. Because of the r, we don't know what it is. We always keep the 0 as the index. So second derivative still goes from 0 to infinity, n plus r minus 1 a n x to the n plus r minus 2. I put everything into the equation. So we have 2x, second derivative n equal to 0, n plus r minus 1 a n x n plus r minus 2. Hope we have enough space for this one. Right, minus the first derivative is this, n equal to 0 to infinity n plus r a sub n x to the n plus r minus 1 plus 2 times y will be that a sub n x to the n plus r equal to 0. Right. Usually we can just combine them if they have the same index and the same power, but I will multiply the 2x inside and the 2 inside. It is much easier to keep track if we have everything after the summation. So we move the 2x inside. Everything else, of course there are 2 here. And we multiply the 2, so we move the 2 inside the x. With that, so we add the power, so we have the plus 1 minus 2, so we add x to the n plus r minus 1. We have to pump the power up by 1 because of 1x. And also I take the 2 inside. It is easier to keep track of everything after the summation, so we don't lose it. Right, notice the first 2 terms here, index are the same, powers are the same, so that's very good. So let's just combine them. I see, they have a lot of things in common. This will be in common. The n plus r actually also in common. So we write the common thing first. The n plus r. Right. And then that's, we'll write that later. The thing that is not common, 2 n plus r minus 1 minus, there's no thing that is not common. Right. Also the common thing is a sub n x to the n plus r minus 1. Right. Right. What we do next is, let's simplify this a little bit. We have n plus r, 2n, 2r, minus 2, minus 1. So 2n, 2r, minus 3. A sub n, x to n plus r minus 1. And then the other summation. Right. Next we will combine these 2 series. It will be a lot easier if we combine them. I'm going to zoom out so we have a bigger picture of things. It will be easier to combine them if we have don't have the r as a power. So I factor out the x to the r just like what we did earlier. And this still the same. A sub n x is equal to the plus r. We will take outside the power of x to the r power, so it will be x to the n minus 1. And this is x to the n only. Now to combine this, it is a lot easier to combine this because when put 0, that series start at -1, and when x equal to n equal to 0, this will start 0. Now we see the difference. This one start at the negative power, and the negative is a reciprocal power, so that's why it is singular point, because it's undefined. Anyway, we need to split out one term. So when n equal to 0, so we just have r n equal to 0. So r 2r minus 3 a of 0 x of -1. Right. By the way, if you solve for initial equation, this will be the same thing as will give us the initial root. It is the same as initial equation. If you do it like what we do here, we should get the same thing. But usually when we do the series, that will show up directly like that. Right. Next, the series will start at 1. Right. Now both of them start at 0. I don't know why I write 2 here, but that is 0. Alright, next, change the index, so this will be x to the k, so we'll change that to x to the k, and we change this to x to the k as well. So yeah, we really need this to be 0, otherwise we have x to the -1. Of course, that is not good. It is undefined at x equal to 0, so that's not good. Right. Anyway, change the index, or we shift the index. N minus 1 equal to k, so n equal to k plus 1. So n is equal k plus 1, so we have k plus 1 in for r, k plus r plus 1, and that is n. Next will be 2 times k plus 1 plus 2r minus 3 a of k plus 1 for n, and x must be to the k. Next part is simple. We match n with k, so pretty much we replace n by k, so not much into this. Now both of them have x to the k, we can factor. I should say combine. I will simplify this first before I combine. So k plus r plus 1, now we have 2k plus 2r, and if we put the 2 times 1 is 2 minus 3 is minus 1, so that's what we have. K plus r plus 1, 2k plus 2r minus 1, a of k plus 1 plus 2ak x to the k. Right, so we've done the difficult part. Now just the easier but more tedious. This equal to 0, initial equation r equal to 0, r equal to 3/2. So we have that. Next we have this relation equal to 0. So we have a of k plus 1 equal to, right, it's going to be -2 over all of this, right, to plus 1. Right, there's a plus 1 here, sorry. Right, this need more space now, so I attach space here. Right, so pretty much now we have this relation. So I will divide this into two parts, each one corresponding to one r values. To the left panel, let r equal to 0, and on this side r equal to 3/2. Now this is the relation. If r equal to 0, we will have a of k plus 1 equal to -2. Now r is equal to 0, so this is k plus 1. Sorry, there's an ak here. Sorry, still ak. So r0, k plus 1, 2k minus 1, because k is equal, r is equal to 0. Right. Next, for this we have a of k plus 1 equal to -2 ak. Now r is equal to 3/2, so we have k plus 3/2. 3/2 plus 1 is going to be 5/2, and then 2k. R is 3/2, so 3/2 times 2 is 3 minus 1 is 2. So multiply the 2 to this side, we actually going to have -2 ak. Multiply by this, you have 2k plus 5 times k plus 1. Right? We factor out the 2 and take the 2 to this factor, so 2k and 5. Right, now we choose some value for k. Let me check real quick and make sure that is actually work, and it look right. Right, so we have that first, and now this is where we start. The index for the problem, it goes from k equal to 0, so that's where we start on both of the series. K equal to 0, put 0 in here, a1 equal to -2 a0. 0 for k, 0 for k, so it is just 1, and 0 for k. One and -1, so we have 2 a0. Look good. That is a1. Now k equal to 1, a2 equal to -2 a1. So we put 1 into k, and we have 2. 1 in for k. That is 2 times 1, 2 minus 1, so it's 1. So we cancel that out. We have negative a1, which is going to be negative 2a0. Look like we have a0, a1, a2, none of them equal to 0, so it's good. We have 3 terms. Yeah, I'm happy with that. Now we go to k equal to 0. K equal to 0, you have a of 1 equal to negative 2. K0, so will be 5 and 1. Forget. Put 0 in here, a to the 0. So we have negative 2 over 5, a0. Now k equal to 1, a2 is negative 2, a1. Now we put 1 in for k here. That will be 2 times 1 plus 5 is 7, and 1 plus 1 is 3. Sorry, 1 plus 1, 2. I look at something else. So 1 here is 7, 2, 14, 2 and 2 cancel out, so we have negative 1 over 7, a0. Sorry, it's a1. And a1 is that. Yeah, we have to write in a0. So it will be 2 over 35 a0. Yeah, so it is just a1 and not a0. Alright, now we have a0 is not 0, a1 is not 0, a2 is not 0. So it's good. We have the first 3 non-zero terms for each constant. So now we have y1 equal to a0 plus a1x plus a2x and x squared and so on. But notice that since r is equal to 3/2, we have to have r to the 3/2. So y1 will be r to the 3/2. a0, we can factor a0 out as well. So we just have 1 a0. a1 is going to be this, but we factor out the a1. Sorry, a1 is this. Factor out the a0. We have negative 2/5x. And then a2 is that. Factor out the a0. We have 2 over 35 x squared. So this is minus 1 minus 2/5 and that. We can call this a y2 or y1. Y1 here is going to be x to the 0 power a0 plus a1x plus a2x squared plus so forth so on. So that is a constant. Is equal to 1. I factor out a0. So be 1 plus a1 is 2 a0. Factor out the a0 already. Just have the 2x. A2 is negative 2 a0. Factor out that. We have negative 2x squared. And then so on. So look right. And the solution will be the linear combination of these two. So pretty much we add them together. And yeah, and that a0 and this a0 might not be the same. So that's why we have the solution as the combination of them. Anyway, yeah, in the y1, y2 fundamental set of solution, we don't really need to have the constant in front. So we can attack the c1 and the c2 into it if we want to. So I write y equal to c1, 1 plus 2x minus 2x squared, and so on. c2, I don't know why I write r, but it's supposed to be x. X to the 3/2 1 minus 2/5 x 2 over 35 x squared, and so on. So yeah, in the fundamental set of solution, we don't really need the constant. So, but when we write the general solution, we're going to have the constant. So it will be like that. Yeah, a little bit long. Usually we find the initial root and the initial equation as well. But if we do the series, the term that go with x to negative 1, that's going to be the initial root. Will give us the initial root. Right. The recursion relation is still kind of the same, but for this case we have two different R values, and we have this, and a lot of other things could go into this, including if we have the repeated root, or if we could have the root that different by 1. So there's a lot of things that go into this. This is the easier one. Anyway, so that was 6. Next we have the general solution to the system. Then we can zoom back in. Right. Right. I do this one instead. It's probably stronger. Right. So let me go into the material needed. Right here. So we need to have the characteristic equation and find the eigenvector eigenvalues for that. So first we find the eigenvalues from the characteristic equation. So we have determinant of the matrix A minus R times the identity supposed to be equal to 0. So we have determinant. Let's just write determinant of 1, 2, minus 1, 0, minus 1, 3, 0, 0, 2, minus. Now we multiply R into the identity matrix. We have that equal to 0, which means we have the determinant of 1 minus R, 2 minus 1, 0 minus 1 minus R, 3, 0, 0, 2 minus R. So we need to have the determinant of that matrix equal to 0. This is a 3 by 3 matrix. The easiest one to do this is use the submatrix, but taking the properties of this is the upper triangular matrix. To find the determinant, just multiply the diagonals. So either it is upper or lower triangular matrix, just multiply the diagonal, and that will be the determinant. So we have 1 minus R, minus 1 minus R, and 2 minus R equal to 0. So we have R equal to 0, R equal to negative, I don't know why it's 0, but R equal to 1, R equal to negative 1, and R equal to 2. So those are the eigenvalues. Are those values. Yeah. Right. Next, so we found the eigenvalues. Next, to find the eigenvectors. So first, for R1 equal to 1. So for this eigenvalues, and we're going to put in the eigenvector equation. So it will be the matrix A minus R times identity matrix times the vector U equal to a 0 vector. So A is 1, 2, minus 1, 0, minus 1, 3, 0, 0, 2. And then minus R multiplied to the identity matrix R 0, 0, 0, R 0, 0, 0, R. The vector U, U1, U2, U3 equal to a 0 vector. And we know R1 is equal to 1, so we actually can say that is 1. So pretty much the matrix will become one minus 1, 0, 2, minus 1, 0, minus 2, 3, 0, 0, 1. Right. Usually to solve this one, use the reduced row echelon form in the matrix. So second, the x to the negative 1. Go to math for the reduced row echelon form. Now I'm going to put this matrix. So usually it's 3 by 4, but since the right side is 0, so it doesn't matter what we do, we always end up 0 anyway. So only need to have the matrix. So I hit alpha and then the zoom key. Bottom menu pop up with the matrix 3 by 3. And OK. The next part is very important. Do not hit the enter key when you put in the numbers. Use this instead. So 0, 2, negative 1, 0, negative 2, 3, 0, 0, 1. Again, we do not need the 0 on the right hand side because it doesn't matter what we do, we have 0 anyway. So like that. If we multiply it out, we will have U2 equal to 0, and then U3. So the first one, U2 equal to 0, the second one, U3 equal to 0, and we don't have anything for U1. So, and besides, there's no 1 in this row, in this column, so we let U1 equal to 1. And as you see later, whenever the column that doesn't have the 1, we're going to choose some values for that. So pretty much we have 1, 0, 0 as this is U, by the way. So that is the eigenvector that's corresponding to 1. Right. And once again, I'm running out of space. Let's try to squeeze here. For R2 equal to negative 1. This time I will go directly to the problem. So again, the equation matrix A minus R times I, unit vector, eigenvector, 0 vector. Right. Now The vector A is, the matrix A is 1, 2, -1, 0, -1, 3, 0, 0, 2. Now I will minus R into the diagonal. R is -1. Let's not skip any step. So -1 for the diagonal. Right, combine the matrices. 1, so that would be 1 plus 1, 2, 2, -1, 0, -1, -1, plus 1, so that's 0, 3, 0, 0, 2 minus, so that's 3. By RREF, so we do RREF here. So second matrix, go to math, go to RREF, alpha, zoom, 3 by 3 is good, click OK. Now we do not click enter anymore, just hit this key. So 2, 2, -1, 0, next, 0, next, 3, next. Once we're done, hit enter. Right, so we have 1, 1, and 0. Right, now we multiply it out. U1 plus U2 equal to 0, and U3 is equal to 0. That one obvious, U3 have to be 0. And let's take a look. We have the 1 here, and the x1, and the 1 here. Those are the first non-zero element, so we cannot mess with that. The only thing we can choose is for the second column, or for U2. So we choose U2 equal to 1. So U1 is -1. So bottom line is we have the matrix, the vector -1, 1, and 0. So that is the eigenvector U2. Next we do for 2. R equal to 2. The equation right. The matrix A, 1, 2, -1, 0, -1, 3, 0, 0, 2, minus. Now we put 2 into the identity, so 2, 0, 0, 0, 2, 0, 0, 0, 2. The 2 will be for the diagonal. Multiply eigenvector equal to a 0 vector. Now simplify this. 1 minus 2 is minus 1, 2 minus 1, 0, minus 1 minus 2 is minus 3, 0, 0, 0. Right, this. I should write smaller. Anyway, let's do the reduced row echelon form for this one. Right, second that matrix reduced row echelon form alpha zoom 3 by 3 is good. Minus 1, 2, minus 1, 0, minus 3, and 3. So we have that. Right, so when we look at this, what we see is the first non-zero element is 1, so we do not mess with that. We do not mess with this. This column doesn't have the leading 1. So in that case, if we have to choose something, we're going to choose U3 equal to something. Keep that in, let's say, keep that in back pocket. But from this equation, we have U1 minus U3 is equal to 0, and U2 minus U3 equal to 0. Now obviously, if we choose U3 to be 1, and then U1 is 1, U2 is 1, so the vector will be 1, 1, and 1. So pretty much when we choose something for the eigenvector, we look at this, and whatever doesn't have the leading 0, the leading 1, this is the first non-zero element is 1. This is the first non-zero in a row, so we have 1 and 1. This column doesn't have anything, so that's why we're going to let that be 1. Same thing here. The first non-zero entry in the row is 1. This one, the first non-zero entry is 1, and then there's nothing here, so we're going to choose U2 to be 1, and that is pretty consistent. And finally, we put everything in the solution. So y, not y. Solution is a vector x equal to c1 e to the r1 t, unit vector u1 c2 e to the r2 t, unit vector u2, and c3 e to the r3 t, unit vector u3. I mean, why say that? It is an eigenvector u3. Anyway, e to the r1 is 1, and u1 1 0 0 plus c2 e r2 is negative 1, so will be negative t. U2 is negative 1 1 0, and c3 e to the r3 is 2. 1 1 1 is the unit vector. So c times e to the eigenvalue times t times the unit, why do I keep saying that, the eigenvector, because I write u, so yeah, so that is the eigenvector that corresponding to an eigenvalues r1. Right, So we have that. So eigenvalues, eigenvector, and the answer in that form. Of course, the formula are going to be on that side. Right. Now we go to number 10. I recorded another question earlier, but I make a mistake, so I have to redo it. Anyway, characteristic equation. So determinant of A minus R times identity matrix equal to 0. Determinant is a number, so that is a 0 number, not a vector. Anyway, so determinant of 4, 1, negative 8, A minus R times that will be R, 0, 0, R. So we will have determinant of 4 minus R, 1 minus 8, A minus R equal to 0. 2 by 2 determinant, that should be easy. 4 minus R, 8 minus R, and plus 8 equal to 0. Or multiply this out. 32 minus AR minus 4R, so minus 12R plus R squared plus 8 equal to 0. So R squared minus 12R plus 40 equal to 0. So be 36 and 4. So yeah. So R squared minus 12R plus 36 and 4. So R minus 6 squared equal to minus 4. So R equal to plus or minus 6. Sorry. R equal to 6 plus or minus square root of 4. Square root of negative 4 is 2i, so plus or minus 2i. So those are the eigenvalues. Right. Now, this is the matrix with real coefficient, so the eigenvalues will be complex conjugate. Good thing is we only need to work with one of them. Right. So let's say for R equal to 6, let's take the plus 2i. Right, now we put in the matrix. The equation. Matrix equation. This is going to be a vector, so a 0 vector. Let me zoom out. Right. It is better. So the matrix A, 4, 1, negative 8, 8 minus R, 0, 0, R, U1, U2, 0, 0. So we have, by the way, R is going to be 6 plus 2i. 6 plus 2i for R. Right. Now we have 4 minus 6 plus 2i will be 2 minus 2i and 1. So 4 minus 6, sorry, is minus 2 minus 2i minus 2 minus 2i, and then 1 minus 8, and then a minus 6 is 2 minus 2i. u1 u2 equals 0 and 0. Right, let's check again. 4 minus 6 minus 2, 1 minus 2i, I mean 4, then minus 2i, and then 2 minus 2i. So it's that. Next thing, usually we do the row operation to eliminate this, but notice that this is going to be the eigenvector, so meaning those two rows are linearly dependent, meaning one is the multiple of the other. So all we need to do is just, if we multiply them out and do the elimination, it will eliminate. So you see. Notice that if we multiply the top by the conjugate, is negative 2 plus 2i. If we do that, so put the calculator in the matrix mode, the complex, and then we do it, because the reduced row echelon form doesn't work with the complex number, so we have to do that by hand. So negative 2 plus 2i is second and the dot, so I do that, multiply by negative 2 minus 2i, that's going to be positive 8, and multiply by 1, as you see those two lines cancel out. Bottom line is we only need to use one column. When this is a 2 by 2, we only need to use one column, and multiply that out, we have negative 2 u1, sorry, negative 2i times u1 plus u2 equal to 0. I said we only need to use the first row, because the second row is the multiple of that. This doesn't matter. Alright, so here we choose 1 to be 0, or I mean, to not do that. I'll choose 1 to be 1. So let u1 to be 1. Then we have negative 2 minus 2i plus u2 equal to 0. So u2 equal to minus 2, I mean 2 plus 2i. Right, now the vector is u1 and u2. u1 is 1, u2 is 2 plus 2i. So when we write like this, we will split into the real and the imaginary. We can always do that. So it becomes 1 and 2, 0 and 2, I. So this pretty much is the A and B in the formula on that side. Yeah. So the reason that we can do this for the complex number because those two lines, those two rows are linear dependent. One is the multiple of the other, so we just need to do that. And finally, we write the solution. The first solution is e to the alpha. By the way, we need to rewrite that. So this is the eigen values. If that is in the alpha plus or minus beta t, beta I, then alpha is 6 and beta is 2. Right, now we can write back the solution, the formula on that side. So e to the alpha 6t cosine beta is 2, and then the vector a 1 and 2 minus a 6t sine 2t times the vector b 0 and 2, and then x2 e to the 6t sine 2t times the vector a minus e to the 6t cosine 2t to vector b. Of course, we do the linear combination of this, we have the the solution. So x equal x1 cx1 plus cx2, and we just put that in here. So that is the case where we have the complex number, and that is number 10. Right. I have to record this problem again because earlier I did and it was a lot more complicated. This is a lot better. Anyway, so far the eigenvalues in this case is complex. We write out alpha and beta. We can use either one of them, and then we have this equation. To solve for that, we can pick either of the row, and then we choose the first row. Then so we have that. Choose one of the variable and solve for it, and then we have that. Right. So that was number 10. So as always, I hope the review prepare you for the test. The final will include everything from the first test review, so this is only a small part of it. So I will end the video here. As always, thanks for watching.